Hello friends, welcome back. In chilled water system, when we go for the pipe sizing, we need GPM value. These GPM values are not same for open loop system, closed loop system. In open loop system also, different GPM values will come based on delta T. In this video, we will see how these different GPM values are coming and technical consideration behind these numbers. Let's start the video. So first we need to understand what is open loop and what is closed loop system. So we will divide this image to three sets. So this is the first set, that is a cooling tower side, and this full setup is the chiller arrangement, and the third setup is the building side. So first we will see the water from the cooling tower. So here the cooled water from the cooling tower enter into the chiller. In the condenser of the chiller there will be a heat transfer. So after that the hot water will go back to the cooling tower again. So this system is called as an open loop system. So coming to the second loop, so here you can see this is the chiller, and from the chiller here we have the building side. So here you can see from the evaporator there is a heat transfer again. So using this evaporator, the cooled water will go to the building load. So the building side we have different equipment like AHU, FAHU, FCU, different equipments are there. So after going to the load, so coming back with the hot water, so this hot water will again go to the evaporator where the heat exchange will happen. So this system is called as a closed system, and this system is called as a open loop system because the water is dropped from the top side. So this is called as a open loop system. So in this example, you can see there is a fan coil unit located here, and the cooled water supply which is given to the fan coil unit is 45 degree Fahrenheit, and coming back, I mean the return side, it is coming with the 55 degree Fahrenheit. So total delta T is chilled water return minus chilled water supply, that is 10 degree Fahrenheit. If you convert this one to degree Celsius, 55 will be 12.77 and 45 degree Fahrenheit will be 7.22. So the delta T in degree Celsius will be 5.5 degree Celsius. So this delta T in most of the chilled water system it will be 10 degree Fahrenheit, but still it is not constant value. If you go to district cooling system, that I will show you now also. So if you go to district cooling system to different countries like UAE, Qatar and different countries, so delta T normally we are maintaining 16 degree Fahrenheit. But so again, so this delta T will be different for different system. So we will have, but most of the HVAC units are coming with the delta T of 10 degree Fahrenheit. So we will show one example with the 10 degree Fahrenheit. Then I will show you a few countries delta T for the different district cooling system also in the same video. So here first delta T we know that is 10 degree Fahrenheit, and we know the basic formula GPM is equal to ton of refrigeration into 24 divided by delta T. So here for example, ton of refrigeration I considered as 1 ton of refrigeration. So 1 ton into 24 divided by 10, the GPM will be, for 1 ton the GPM will be 2.4 GPM. So now first we will see how these 24 fixed values are coming in this formula. After that we will see this is for the closed loop system, and for the open loop system also we will see how the different values are coming for the GPM. So first we will start with the 24 value verification. So first we all know the basic formula, Q is equal to MC delta T. So here the Q means HVAC unit capacity, that can be chiller capacity for example. So it is in kilowatt, and the M mean that is the mass flow rate. So this M is the mass flow rate, and we have the C. The C is the specific heat of water, that is 4.187 kilojoule per kilogram degree Celsius, and we have the delta T. Delta T means you know that chilled water temperature difference, the supply and return side temperature difference. So you can rewrite the formula in this way. So here density is equal to water density, this which is the constant value 997 kilojoule per meter cube, and the Q value from here you can find out, that is the water flow rate. This is what we are going to find out to verify 2.4 GPM how it comes. So this is in meter cube per second, and here again C, the same value is specific heat of water, and delta T is the temperature difference. So now we are going to apply all the values in this formula. So first we know that Q is equal to, we are going to consider 1 ton for this example. So 1 ton in the Q, and you know that 1 ton is equal to 3.517 kilowatts. So I round up to 3.52 kilowatt, and so density is the water density, that is 997, and Q value we are going to find out the flow rate, and C value you know that this is the specific heat, that is 4.187, and delta T I kept the delta T as same. So here now I just want to rearrange the formula. So what I am going to do, the Q is equal to all this value I'm going to bring to the downside here. So 110 into 3.52 kilowatt as a constant. Then these two, if I multiply 997 into 4.187, I will get the answer of 417.414. And here delta T I kept as same. I didn't change anything now. So after that, I'm going to make the value here. So here you know that the Q value, now we have the answer in meter cube per second. So I need the answer in GPM. So I'm going to divide with 15850.3 GPM in the same answer. So here you can see the difference. So 110 into 3.52 kilowatts still same. So 417.4 divided by this answer, and delta T still I kept as a constant one. So Q is equal to 110 into 3.52 divided by, if you divide these two answers, we will get 0.263, and this answer will be in the delta T. And here you can find out. So Q is equal to 110 into 13.3, because of if you divide these two answers, we will get 13.3 divided by delta T. So now you can see Q is equal to 1 TR into 13.3, and delta T, we know that in our example 12.77 return temperature and supply temperature is 7.22. So total delta T is 5.55, and finally you will get the answer. Q is equal to 1 into 13.3 divided by 5.5. Q is equal to 2.4 GPM. So for the 1 ton of refrigeration, we are getting the answer of 2.4 GPM using these basic formulas. So as I told you earlier, this 2.4 GPM will come normally if the delta T for most of the HVAC system we are keeping as 10 degree Fahrenheit. But this is not the same for all the area. For example, if you go to the district cooling system, so here I have one example. So this is the district cooling system from the Qatar. So Qatar normally they are operated by the Qatar Cool, and here you can see the delta T. So this is one of the HVAC unit schedule. So this is the HE, means the plate heat exchanger. So here you can see these two sections. So the first section, this is the district cooling system. District cooling system, water in and out. That means there is a central plant. From the central plant, we have the incoming water and which is going outside also. For example, this is the incoming. So this temperature first we are entering as a district cooling side, and from here this will go to the plate heat exchanger. Again coming back, this will go back to the same system. So this is the this is the inside from the central plant, and this is the building side. So here first we will see what is the temperature in the central plant side, and after that we will see the building side. So here they have given district cooling side of 5 and 14 degrees Celsius, and the building side they have given 15.2 and 6.2 degrees Celsius. So again going back to the same example, so here we can see the temperature is 5 degrees Celsius at this point, and going back with the 14 degrees Celsius. And coming to the building side, the building supply temperature is 6.2, and the building after the load, the temperature coming with 15.2 degrees Celsius. So here if you see the primary side and secondary side, so the delta T, if you check with this secondary side, it will coming like delta degree in Fahrenheit is equal to 16 degree, and delta T if you see in this degree Celsius, this is 9 degree. So as I told earlier, most of the HVAC system has delta T in Fahrenheit is equal to 10 degree, but if you go to district cooling system, normally the delta T value will be higher. So I will explain the same thing with the UAE code also. For example, here you can see in the UAE code, this is the primary side in the district cooling side, so that is 4.4 and 13.0 degrees Celsius. Normally when you go to the secondary side, at least 1 degree higher temperature will be there. For example, here it is 4.4 mean it is 5.5, here it is 13.3 mean it is 14.4. if you see the delta T in the, this is based on the UAE, so if you see the delta T here also it is 16 degree Fahrenheit, Celsius also 9 degree. So the delta T overall it is same like Qatar and UAE, but the temperature, internal temperature, it is different for both the countries. So in this case, what will happen? The same formula we will use, that GPM is equal to ton of refrigeration into 24 by delta T. So here in the delta T, instead of 10 degree Fahrenheit, you will use the 16 degree Fahrenheit. If you have, just now I showed you the delta T for the Qatar and UAE. So there you will use the delta T of 16 degree Fahrenheit. So what will be the changes will happen? Same 1 ton of refrigeration into 24 divided by, there in the example it was 16 degree Fahrenheit. So if you apply that one, so we need to consider 1.5 GPM instead of 1 ton is equal to 2.4 GPM for the district cooling system based on the different countries. So now we discuss about the concept in the closed loop system. So it will be 1 ton is equal to 2.4 GPM or 3 GPM based on the district cooling system or chiller system, different system like that. Now we need to see, coming to the open loop system, normally we see that the 1 ton of refrigeration is slightly higher. So because sometimes 1 ton of refrigeration is equal to 3 GPM compared with the open closed loop system, the open loop system has higher GPM. So we need to know how these higher system values are coming. Hello friends, 1 minute. We worked hard to collect all the information from various sources to give you best understanding of the subject.
Most of the people watch the video but they don't subscribe. Please motivate us by subscribing our channel to post more and more technical videos for you. Thank you.
So we all know that normally 1 ton is equal to 12,000 BTU per hour. So the Cooling Tower Institute or CTI, this is the agency, is responsible for developing the rating system for all the cooling tower, has mentioned that the cooling tower ton is 15,000 BTU per hour, not 12,000 BTU per hour. That means 12,000 BTU per hour refrigeration ton. Additionally, they are adding 3,000 BTU per hour, that is for the compressor heat. So 12,000 plus 3,000, total 15,000 BTU per hour they are considering for the open loop system. So because of this additional BTU per hour, the open loop system GPM capacity is considered as higher. So we will explain slightly detailed way so you can understand easily. So as I mentioned, a refrigeration ton is equal to 12,000 BTU per hour. A cooling tower ton is equal to 15,000 BTU per hour. The extra 3,000 BTU per hour is carried over from the refrigeration cycle. So if you see this chiller arrangement, normally we have 4 major components. So that's a compressor, and here's a condenser, here's the expansion device, and finally the evaporator. So here when the refrigerant enters the compressor, this refrigeration in low pressure and low temperature gaseous state. I mean at this level it will be low pressure zone. After the compressor pumps up the refrigerant into the high pressure and high temperature state. So this process requires energy, basically adding an average of 3000 BTU per hour of compressor heat to the cooling tower load. So this comes from the assumption that compressor generates 3000 BTU per hour in a typical air conditioner system that the cooling tower has to dissipate. So because of this additional 3000 BTU per hour coming from the compressor load, so this 3000 BTU per hour has to be removed by the cooling tower. So that is the reason instead of 12,000 BTU per hour, we are adding additional of 3000. So it becomes 1 ton is equal to 15,000 BTU per hour. So if you say that in the normal case 1 ton is equal to 12,000 BTU per, so in the open loop system it will be 15,000 BTU per hour. That means 15,000 divided by the normal capacity 1 ton is equal to 12,000 BTU per. So it will be 1.25. That means 25% higher flow rate compared with the normal case. So if you say 1 ton is equal to 2.4 GPM in the normal case, when coming to the open loop system it will be higher like 3 GPM. So I hope now you understand how the open loop system and closed loop system different GPM values are coming. So thank you for watching the video. We will see you again with another interesting topic.